Hello everyone, my name's Sam Price and I'm currently a software architect with Family's Own Cyber Safety. Over the last probably 6 or 7 years or so, I've had the opportunity to be involved with systems that have needed to scale, quite often scale quite considerable amounts. And through those experiences, there have been lessons learned, observations and changes to daily routines. And it's the latter bit that I'd like to talk a little bit about today. So how I've changed my daily routine to keep performance in mind. Okay. Now, before we get into it, I just wanted to say thank you to all of our amazing sponsors. DDDPerth, as an attendee, has always been my favourite conference, and it wouldn't be possible without all of the sponsors. So thank you very much for supporting local Perth talent. Why practical performance? Well, I'm going to suggest a few reasons that companies that I've worked for value, but then later suggest one of my own. Our customers. Without customers, we can't make money, typically. And so we need our customers to have compelling experiences. Now, Jacob Nielsen was actually a very well-regarded usability expert, and a lot of the UX design principles these days are actually based on his foundational research. If you do a quick Google search, you'll find many statistics on what happens when sites are unresponsive or apps take a long time to load screens. And I'm sure we've all seen these kinds of things before, so I've just selected a few random stats, both from Google, in the hope that you trust that they're real and true. Why else? Low operating costs. These days, infrastructure hosting is a major expense for a lot of companies, and particularly in the new world or newish world of cloud, it's very easy to inadvertently dial up how much you're spending. And so I'm hoping that through good performance practices, we can keep our costs a little bit lower. And I think we all may have experienced this kind of thing before, where the easiest thing to do is to vertically scale, but it's not effectively the most cost effective. And so if we have good performance practices, quite often our software will end up performant too, which typically keeps our costs low. And the final reason is that I've observed that a lot of software engineers don't necessarily include practical performance practices in their daily routine. Now, I don't necessarily blame them. I think this is sort of the classic quote, premature optimization is the root of all evil. I think most of us have heard that, and it does discourage us a little bit from thinking about performance. And now Sir Tony Hoare actually expands on his often misquoted quote and explains that really we shouldn't think about micro-optimizations 97% of the time, but instead spend that 97% of the time with good software design. So what algorithms and data structures we're going to use, how we'll design APIs and things like that. Performance principles I personally use when I look at my day-to-day work, but then also when designing solutions. And I'll present two principles that I use. So the first one is craftsmanship, which is really well-designed software systems using modern technologies and processes will outperform systems built in an ad hoc manner without good process. Much like how craft beer outtastes factory beer. So what does it mean to practice craftsmanship? So firstly, we need to understand our customers and our users, how they're using our software and what they need. We need to understand our programming languages. We need to understand what third-party, technologies that our software solutions integrate with. So databases, caches, queues, various other bits and pieces. How is our software being run? Are we running it? Are we using Linux as an OS, or is it an EC2? Maybe we're using Kubernetes for orchestration. And then sort of the glue that holds all of this together is good old computer science theory. So from human-computer interaction for our users all the way through to data structures and algorithms. And so to exhibit craftsmanship, it'd be wonderful to be an expert in all of these things, but the reality is that's not going to be possible. And so we'll each have various skill depths. But really, I think what we kind of need to do is to, as software engineers, spend a little bit of time to understand our tools so that we can hopefully write performance solutions that are good for our businesses and customers. And so how might we do this? We're all busy, we've all got different routines. And so I'd suggest that actually what we want to do is narrow our scope. So don't try and understand every aspect of a database. Instead, just focus on one little thing. Similarly, factor in time for planning and learning. So some of us might be practicing agile, and so when we do estimation, it's nice to bump that up a little bit if we want to go and spend time to deliver something quality. And obviously, anything that we've learned, we wish to apply during the implementation phase. Now, here's an example of where, I guess, a team that I've worked with, where we had a lapse in craftsmanship. There were two services that communicated to each other, both via HTTP. One service used an HTTP library called Apache HTTP Components, and we brought that in its default configuration without reading the manual. And the manual very clearly states, no more than 2 concurrent connections per given route. So that means I cannot have more than 2 threads making requests to a single URI on a single host. Which is actually very limiting, and that proved to be the case for us. And sadly, this happened twice. The other principle that I wanted to introduce is less is more. I think a lot of us would have heard of that before, but the idea here is that a system that does less is more performant than a system that does more. And certainly in the sort of ultra high performance sort of category, really high-performing systems have almost no features. They do one thing and they do it very well. Now, what are some examples of less is more? I could probably write a list of about 50 things here, but I'll keep it fairly limited. One of my favorites is complexity. So KISS holds true, and at all levels as well. So from the level of actually writing code, if you're using a compiled language, for example, the compiler will often optimize your code, and the compiler does a better job of optimizing simple code than it does complex code. All the way up to maybe a service level. If you've got a fairly simple service, maybe it's a microservice, but it has some deficiency, it's much easier to replace that service than a horribly complex monolith. And so I'm not advocating either way, by the way, for monoservices or monoliths or microservices. But yeah, this list goes on, but I won't go through all of these things. And here's a classic table from the greater internet. Some of us may have seen this before. The thing that I like about this table is it enables me to understand what happens when my software is run through the eyes of the computer a little bit and how long various things take. But to make it a little bit more clear, I thought it might be fun if we pretended that we're in Perth, and for us to go to the level 1 cache is just one simple step. But then for us to actually send 2 kilobytes over a gigabit network, well, that's like us going all the way to Fremantle and back. Well, what about if we wanted to read a meg from memory? That's like us going to Dunsborough and back. It's quite a while. Us going just to Dunsborough, quite a while. And then finally, a single packet from Perth to California and back to Perth again, halfway to the moon. So if we think about these things when writing software, it puts things into perspective a little bit. So this is an example where we leveraged less is more. So the context here is that we had a native library that filtered network traffic. Now, I've ported that code and simplified it to Java. And this library, it runs on our Wi-Fi routers, but we wanted to reuse that at the end of our VPN. And so all of a sudden, the environment has changed. We went from 20 queries per second, really, to about 2,000 queries per second. And our poor little filter client library did not like it. So this is the code beforehand. And after looking at the code, we made a simple change. Did anybody see it? So anyway, we changed a tree map to a hash map. So why would replacing tree map with hash map make a difference? Well, obviously the synchronized block itself is a bit of an issue, and it's mutually exclusive and blocks all but one thread. And that one thread spends obviously too long from getting a decision from the cache. But why still? Why does it take so long to get a decision from the cache? And to be fair, it doesn't actually take that long. But the difference here is that tree map is based on a red-black tree, and hash map is based on a hash table. Now, I realize at this point, not everyone in this room has probably studied computer science and knows about big O notation. So that search column is big O notation. And it says that a red-black tree runs in log n time and a hash table runs in constant time. But what does that actually mean? So the next two columns are, if I have a cache of size 100 and a cache of size 100,000, how long does it take me to look up my item? Well, if we're using the tree map, I may need to look at 6 elements before I find the one that I'm looking for, if there are 100 elements in the cache. But if that's 100,000, then I'm going to need to examine 16 elements. But our good old hash table, I can find the element that I'm looking for immediately, regardless of the size of the cache. All right, so principles are done, but what are some of the performance issues that I've observed over the years? And this sort of hopefully adds some credibility to this talk. Software engineers, that is a bit of a joke, but they are the people that write the code. All right, databases. This happens all the time. Indexes, they're either missing or misconfigured, they've got the wrong columns or the wrong column order. Now, I think there could be multiple reasons for this, like the worst being negligence, but quite often I think it's more of a maintenance issue where we change the code at the application layer, but then we forget to actually go back to the DB and update the indices to match. Similarly, we have, each team has individuals of different levels of experience, so less experienced people may not know about indices, and they also may not know about things like database query plans. And then finally, a little bit less column, but I've seen a fair bit of database misuse. So because we have a relational DB, we may as well use it as a document DB. Or maybe we just need somewhere to aggregate data, so let's just use the relational DB instead of using, say, a stream processing engine. So there's quite a few examples there. And probably my favorite of all is traditional ORMs, so object relation mappings. This enables us to write software without actually having to write database queries. We just use higher level constructs, and the ORM will take care of SQL generation. Now, the primary issue with ORMs that I've observed is that the DB interaction is opaque. So we don't see what SQL gets generated. We don't know if it's efficient, and we don't know how many times statements are being created and run. And there's a very common problem called the M+1 problem that I won't detail here, but it's easy to solve, but it's just something to be aware of. And then the final performance pain with ORMs is select star. So whenever we use an ORM, it always brings back every column of every table, even though we mainly care about 3 fields. And if we roll this all the way back and think about our users, a good user interface, it only shows the information that's relevant and nothing more. So we should treat the DB the same way, really. The final common performance issue that I've observed is network ignorance. And this kind of goes back to the whole less is more thing, and putting ourselves in the place of a computer and think about the different latencies involved. The network isn't particularly quick, so we should try and avoid it. But yet, too often we see many network calls when only one is required. And here is here's an example, very simple, and this is in JavaScript. All we want to do is find all the devices that are in a family. And so we load all the family members, and then we iterate through them, and then we load the devices for each family member. This is very slow. It's not a great way to do it. So I would encourage us to think about having as few network calls as possible, and ideally a single call that can do everything that we want. And actually, this is why GraphQL, for example, is very popular. The other one is large payloads. So quite often, again, if we're using an ORM, we might get everything back. If we've got a RESTful web service, we might get everything back. And particularly if we're showing report data or tabular data, we might just do the simple thing, which is bring everything back. So large payloads are more tolerable on fast networks with few hops, but as soon as the internet's involved and traversing the public internet, large payloads become very slow. A reason for this is the TCP window. So most HTTP is based on top of TCP, and TCP will only send a certain number of bytes to the client before waiting for the client to acknowledge them. And then after it gets the acknowledgement, it will then send the next chunk of bytes. And so each one of those is effectively a round trip, and it can add up if you've got a very large payload. All right, no talk on performance would be worthwhile without a war story. So this is a reasonably recent one. So last year, Family Zone experienced a period of rapid growth. So these are unique visitors. And so we went from about 15,000 in March 2020 all the way through to almost 1.5 million by the end of the year. And this is a wonderful way for teasing out performance bottlenecks in your system. So one of those bottlenecks, we have a classroom product. And inadvertently, this was also one of the reasons why we grew so much, is that COVID struck and our product, teachers could do remote learning. So the teacher could be at home, the students could be at home, and the teacher could create classes and interact with their students. So what this screenshot is showing is the teacher's view of the world, and each tile is a student's desktop. So the teacher can keep track of what their students are doing and make sure that they're all doing mathematics and that little Johnny isn't off at YouTube. So an approximation of part of the architecture is this. So we have the teacher's browsers on the bottom right corner, and up the top left we have an ingestion API. And so that ingestion API is constantly receiving screenshot data from laptops. And it does two things. First of all, it stores the actual image data in Redis, which is the screenshot cache there. And then it publishes an event. So anyone that wants to know about that screenshot can be informed about it. And really the only subscriber of that event is the teacher's browser. So hey, little Johnny's watching YouTube, a new event arrives, the teacher's browser makes a request to the API, to the data service, and to Redis to fetch the fresh image. Now, when we first experienced the growth, our event service got destroyed, and I'm not actually going to talk about that. But and so as you can see here, we had 1,500 events going in, and only 150 coming out the other side. And this was actually a terrible, terrible experience for our teachers. They couldn't effectively conduct remote learning sessions. So we replaced the event service, but then something else happened. Kaboom, Redis caught on fire. and I've seen this many times actually. You remove one bottleneck to discover another. So what did we do? So the good news is we had thought a little bit about this, and we're like, there's going to be more events hitting the teachers' browsers, so why don't we just queue them up, send it, and then create a batch request and send that off to the API so we can load multiple screenshots in one go. We did that, but then Redis caught fire. And so first of all, personally, I screamed at the impossible because I've used Redis a lot and I've never destroyed it before. So this is a first for me. Now, we had to resolve the customer issue immediately because it was effectively a complete outage to people using the classroom product. So we actually added in a dynamic throttle to our event service, which is just handcrafted code that basically just dropped a percentage of screenshots. And so we could turn it up or turn it down at runtime. And so we would follow the production load, and when it got too much, turn it down a little bit, turn it down a little bit. And that was really good, but also very sad as a developer. You never really want to limit the capabilities of your service. And obviously we commenced investigation. So what did we observe? One minor observation was that our data service was a bit slow and needed replacing, but that data service was horizontally scalable. So whilst it wasn't wonderful, we could spend a bit more and still be online. And we were just using Redis as a vanilla key value cache. And for those that don't know, Redis is actually single-threaded, sort of much like Node. And so, there's no contention there. It's just a single thread that does all the work. And we noticed that the Redis CPU was actually at 100%. So something's definitely going on here. Now, fortunately for us, we had a dashboard and we had the Redis commands on our dash. So we knew which commands were being used, and there were only 4: put, get, multiple get, and keys. Now, multiple get was interesting. So this is when the teacher's browser calls back with a collection of students and says, get me the screenshots for all these students. But in this case, there might be just 10 students at absolute worst and 5 keys, so that's 50. So that's not super expensive, but then keys in itself, though, this is the number of items in the Redis cache, the number of screenshots that we have in there. And so there's 100,000 of those probably. And so that is dubious. Why are we calling keys? So we weren't the authors of the data service, so we dug a little deeper. So it turns out that a single user can have multiple windows. And so that could be another monitor, or maybe they've got separate Chrome windows. But each of those ends up, we get a different screenshot for each of those. And so we used user ID plus window ID as our cache key in Redis. And so if we looked at the data service, we would see some pseudocode that says, hey Redis, get me all keys that match this user ID. And then I've got my set of user IDs. Hey Redis, can you please get me all the screenshots for these users? So the first one is horrible because we may have to, Redis may need to iterate through 100,000 cache keys. And then the second ones we can deal with, that's absolutely fine. So we know we need to eliminate keys, but how are we going to do it? So we were using Redis as a key val, but fortunately Redis also supports hash tables as the value. And so what we can actually do now is say our key is just the student or the user ID, and our hash table, the key within the hash table is the window ID, and then the value is the image data. So what effect did this have? Well, Redis was a lot happier. And so we can see that we've got two network calls have become one, which is a win. And similarly, the actual Redis operation, hgetAll or hashgetAll, there's very few keys that we're actually examining with that. So it's effectively constant time lookup for us. So we went live with this change, and all of a sudden we started receiving feedback from support that our customers are happy again and everything was resolved. So it was a big win for us and our support staff and also the sales team. But we had observed that Redis was still operating at about 70% CPU. So we're putting it under pretty high load. So we had some further work to do, but fortunately we could spend our time here and actually do a little bit of research and plan out how we wanted to attack things. So we replaced standalone Redis with clustered Redis. We actually replaced the data service with a screenshot service, which was much more performant. And then all the way through, we effectively used streaming. So in the case of Redis, we used Redis pipelining for streaming, but then in the case of anything that was HTTP, we used chunked encoding, and that enabled us to keep our memory under control and not actually have to allocate or bring the entire classroom full of screenshots into memory for our API. So our job's not done though. Just because our customers are happy, it doesn't mean we have things to do. So we need to have a retrospective. So what went wrong here? Well, first of all, I personally made the mistake of not doing proper analysis and load testing of the screenshots API. And the reason for that is in part because I'd never broken Redis before. I didn't think it was breakable. Another observation was that good observability really did enable us to resolve this problem quickly for our customers. And that in turn gave great confidence to our support and sales teams. The other one was that a root cause fix here, we knew that this problem was done and dusted with and it wasn't going to come back to bite us. We might have future problems, but we were satisfied that this same issue wasn't going to recur. Another observation was that Redis has excellent documentation. Every single Redis command, they provide us the big O notation. So as software engineers, we know how our code is going to perform when we interact with Redis, assuming we've read the manual. And then finally, simplicity. Again, going back to this, keep it simple, stupid. The data service was really easy to replace with the screenshot service. And so, again, I felt that whenever we do future software development work, just, again, try and keep everything really simple. Okay, so covering all of these issues, how can we apply the performance principles to our day-to-day routines? So the first thing for me is documentation. And I know documentation in some ways is a little bit of a dry subject, but I think we should document service level objectives. So a service level objective is really a contract between you and your customer. And that might be from a service being the customer of another service, or a human customer interacting with your website. And so work with your user experience team or your product management team and define what your SLOs are. So do you expect all of your pages to be fully rendered with under 2 seconds? Maybe, you probably should. In that case, make sure that that's widely known and documented. Similarly, with new features, make sure that we write SLOs into the acceptance criteria. And different features, for example, will have different SLOs. So if you've got a search API, you're going to want that thing to be pretty quickly. Users are going to expect to see results quickly, so make it quick. But then something like a reporting job, it's absolutely fine to take your time. Right, what else can we document? Database index usage. So it's a really simple one, but if you've got code that interacts with a DB, document the index. I firmly believe this helps with long-term maintenance. Plus, it's a really good educational piece. So newer developers, or less experienced developers coming into a team will see this, and then they'll be curious and ask questions or look at documentation. So it's very, very useful. Okay, now here's another example. If you, as a software engineer, have thought about the performance implications of your code, and there's something that you should point out to future readers, document it. So this method here is a very simple method that looks through a collection of intervals and determines whether any of those intervals contains the current time. So that could be the future time as well, actually. So it's a poorly named variable. So how could we document this? So in our case, we might be using this to determine whether or not a teacher has a class that's active right now. But we know that a teacher is never going to have more than 100 classes. And so we're super happy iterating through 100 items, because that will never, we're confident this will never become a performance pain for us. And so we know that it runs in constant time, but hey, if we used an interval tree, then we could get log n, which would be much, much faster. But interval trees aren't in the JDK, and we're never going to use this with more than 100 intervals, so it doesn't matter. But we can go better still. I know a few people in the audience won't be liking this one, but we should be logging this as an error because this method was designed only to support 100 intervals. And hopefully we have monitoring on our monitoring and alerting on errors in our logs. So if we get pinged about this, whilst we might not have a customer issue, we can prevent a customer issue from occurring. Or similarly, this could actually, we may have 100 intervals because we've got bad data in our DB. Something else has changed and all of a sudden we've got more data than we need to. So these kinds of statements can be very, very useful. Right, observability, super, super useful. Now, what that really means is that us as software engineers, if we're looking at logs and metrics and traces, we should be able to have a reasonable idea or indication of what's going on with our software and systems. That may not always be true, but most of the time we should be able to. Why would we want to do this? Well, if we've got things to look at, we can look at them frequently, and that enables us to become familiar. So we know what usage patterns service A has and at what times of the day. And if we're looking at it frequently, we know what it looks like normally, and if we notice anything different, then we can dig into that proactively. Similarly, if we do have an outage, and actually whether or not it's related to performance, we can improve our mean time to resolve by having excellent observability. And the final point here is just that in this day and age, a lot of our systems are quite complex, so we might be talking to Redis, we might be talking to a database, we might be using PubSub. There's lots of things all commingled, and maybe we're orchestrating with Kubernetes. In this complex system, there are many unknowns. We don't know how our system's going to fail, but if we've got good observability, when unknowns do come up, we can normally convert them to knowns fairly effectively. So what do we need? And sadly, there is no perfect answer here. It really depends on what the thing is. Are you trying to observe a web page or a mobile app, or are you trying to observe something that's server-side? Yeah, all of these things have different requirements. And how is that thing being used? You know, is it critical? What does it mean for your customer if you have an outage? And then finally, what's your budget? Because some of the tools are expensive. So yeah, sort of as mentioned, there's many kinds of things that we could also measure and monitor. I won't go into those. Now, this observability triangle really goes from the top, which is the best of the observability, but it's also the most expensive, either through dollars, or where dollars may be just cash, or dollars could be time. So APM stands for Application Performance Monitor, and this gives us wonderful insight into our existing services. And next down the list, we've got boundaries and boundaries, which basically just means whenever your application speaks to something else, or you cross a tier within the application, that's a boundary, and so you should measure around that to understand what happens when you cross that boundary. Similarly, it's critical to be able to heap and stack dump. They're very useful, and there's different ways you can do that, but definitely worth doing. And then the simplest and cheapest of all is just making sure that you've got rudimentary metrics and monitoring over critical paths and endpoints. And I'll just jump on to what an APM actually looks like, because not everyone may have seen them before. And I stole this image from Datadog's website, and I should also say that whilst we are a Datadog customer, we don't use Datadog APMs because they're expensive. So all of a sudden we can see inside a particular service, and we can see where we're spending a lot of time, like which method we're spending a lot of time in. And us as developers, we know whether or not this is an issue. I might be expecting to sleep a lot, so that's okay. But it just gives us so much insight into our running application. Now, this is an example of where, in a previous life, New Relic has an APM as well, and New Relic saved us. So we had some code that I worked for an e-commerce company, and our service was responsible for showing prices on all websites and all mobile apps, and we had many millions of active users. And what had happened is there's an API layer managed by another team that was above our service, and they were moving from a caching to a non-caching architecture. So our service used to get about 250 requests per second, but then over a period of a few months got up to about 25,000 per second. And so anyway, we noticed that we'd started to slow down and our metrics had blown out, and we got alerted. And so we jumped into New Relic and had a look. And the bit of code that it pointed to, I looked at this, load deal, yeah, I know it's going to be talking to the DB. It's always the DB. It's going to be find by ID. Wrong, it was not. Our DB was fine, our connection pooling was fine. Instead, we were using Java 6 at the time, and the currency class within Java 6 is actually pretty inefficient. And the get instance method actually takes out a global synchronized lock. And so only one thread can execute that. Now, fortunately, it is using a hash map, so it does run in constant time, but still, there is so much contention on that lock amongst other threads that this was a major bottleneck. And New Relic pointed us exactly to where that bottleneck was, and we were able to resolve that in under an hour, actually, and get the prod fix out. And so that's excellent, mean time to recovery. Now, we are coders, and hopefully we all do code review as well. Maybe we pair program. And so really these practices apply equally to both. I think the first and most important one, or at least it depends on what you're doing, but always consider growth and scale. Like, what's our sales forecast? Like, how many new customers are we going to have in the future? What if we have 10,000 things instead of 10? Is there any unnecessary I/O or connection? If I'm writing code that interacts with a database, if I'm using Hibernate or another ORM, well then make sure I'm logging SQL and run query plans against the output SQL. There's a lot that we can do. All right, so this example was fairly recently. At Family Zone, we introduced a new database technology, something called CockroachDB, which is a horizontally scalable relational DB. It's very cool tech, but we'd never used it before. And so we had a really simple relationship here. It's a many-to-many relationship between users and guardians. And so fortunately, the software engineers in the team, they decided to load up this database before we got anywhere near production with data, and then run some query plans. And they quickly saw that what they thought would be a really quick query actually scanned 28,000 rows. And so this was strange. They've just got a very simple many-to-many relationship. They've defined their foreign keys. What was going on? And so as it turned out, different databases have different characteristics. And one of Cockroach's characteristics is that when you create a foreign key, it doesn't automatically create an index on the column referenced in the foreign table. Not all DBs do, but they hadn't experienced it before. But fortunately for them, they did their due diligence and ran query plans, and they added the index and got their estimated row count down to 1. And the thing I like about this is it was spending time with the new technology, reading the manual, working through it, and this would definitely have become a production issue if they hadn't have done this, because we were going to load this up with about 3 million students, and it was going to be hit a lot. So that's it for me. Thank you very much for listening. Just to kind of recap, I introduced a few principles and explained how I think they help us to derive good practices as software engineers. Hopefully some of this was useful to you. Thank you very much.